Hello everyone, my name is Primrose Pineda. On behalf of Park System Southeast Asia, we'd like to thank you for joining us today for the first session of our webinar series on nanoscale research using AFM and techniques, principles of AFM imaging modes. Before we begin, let me give you a quick overview of today's session. The presentation will take approximately 30 minutes, which should allow us some time for a few questions at the end. Your mics have been disabled by default to give our speaker an uninterrupted speaking experience. If you click the raise your hand button at the end of the talk, I can unmute your line so you could ask the question. Or if you would prefer, you may type in any questions that you have in mind using the question module on the GoToWebinar dashboard at any time during the webinar. After the conclusion of the talk, we will then go back to the series of questions that we received. We'll answer them in sequence to the best of our ability. If time does not permit for all the questions, we'll send a follow-up email to attendees to answer those additional questions. At this point, I would like to give a short introduction on our speaker. Chris Jung is an application scientist for Park Systems Korea. He received his master's degree in physics from Kyung-hee University and his bachelor's degree in physics from Dankook University in South Korea. His major project includes evaluation of Kelvin probe force microscopy at the perspective of resolution. Without further ado, it is now my pleasure to introduce our speaker for this webinar, Chris Jung of Park Systems.
So, hi everybody, I'm Chris from Research Application Technology Center, and I'm going to have some speech about the principles of basic AFM modes today. And these are the contents for today's webinar. At the first chapter, I will give you some introductions of fundamental theories of AFM. And then, at the second chapter, I will treat deeply with 3 different basic AFM modes. And finally, at the last chapter, some image of 3 different modes will be discussed. So first, introduction. Let's see what can we do with atomic force microscopy and study about atomic forces which we use for AFM measurement. What can we do with atomic force microscopy? Using AFM, we can measure the topography with atomic forces between the tip and the sample. And also, we can get the electrical, mechanical, and thermal properties as well with that at the same time. Then, what is atomic forces? Imagine there are 2 atoms in a space. If they have a distance, there is attractive force applied between 2 atoms, which wants to make 2 atoms closer. So, due to the attractive force, distance decreases like this. But when they get so close, repulsive force push each other to the opposite direction. So we use these 2 kind of forces for AFM system, the attractive force and the repulsive force. This curve called Leonard-Jones potential, and we can see the relation between the potential and the distance between tip and sample. Think like there is an atom at the tip end, and the other is on the sample surface like this. I just express atoms with these sky circles. So when the tip is so far from the surface, there are no big interactions. But when the tip gets closer to the surface, it feels the attractive force. Of course, the repulsive force is at every distance as attractive force does, but at that distant region, attractive force is more bigger than repulsive force. So we use this region for non-contact mode. And if the tip gets more closer to the surface, tip feels repulsive force more than attractive force. So we use this revision for contact mode. So again, we use attractive force for non-contact mode and repulsive force for contact mode. Chapter 2, Basic AFM Modes. And so in this chapter, first we will study about the set point and feedback, which is very important things for understanding AFM measuring. And then we will see 3 different modes of AFM starting from the contact mode. So to understand how AFM works, we need to study some important values, and the set point is one of them. For AFM imaging, we need the reference value. In AFM system, we call this reference value as a set point. And the values we use for set point are very different depends on which mode that we use for. In contact mode, we use force as a set point, and we use the amplitude for non-contact or tapping mode. This is very easy approach to understand what set point is. Think like you are in the air balloon with a fixed focal length camera, and you have to picture the roughness of ground without any focus out. What can you do in this situation? The answer is just moving the air balloon up or down during picturing the ground, like this. Then you can get the perfect image without any focusing out. So in AFM, air balloon is the scanner, and the fixed focal length is a set point. And the feedback is another important thing as well in AFM system. It is the process which maintains constant imaging conditions by adjusting the scanner positions between the tip and the sample. It works by monitoring the error signal, which is calculated by difference between the PSPD's current signal and the set point, and always keep the error signal to the 0. So from now, we will see 3 different basic modes starting from the contact mode. So first, contact mode. Contact mode uses the repulsive force for the feedback. When the tip has a physical contact with the sample, the repulsive force is applied on the tip, then the cantilever bends because of it. So the position of the laser dot gets higher than that of initial state. So in contact mode, bending of cantilever varies with the repulsive force change between the tip and sample, which leads change the position of the laser dot on the PSPD. The tip bends more when the repulsive force gets bigger, like this. This is the state of the node interaction, but at 10 nanonewton and at 100 nanonewton, tip bends more like this. So 100 nanonewton has more cantilever bending than a 10 nanonewton set point. So we need to set an appropriate reference force for the AFM measurement. This is the scheme and procedure of contact mode. First, AFM tip is in physical contact with the sample. Then the cantilever bends by the repulsive force between the tip and sample. Reflected laser dot on the PSPD goes up due to the bending of the cantilever. So feedback moves the scanner up and down to maintain the constant bending of the cantilever. So finally, the scanner position follows the sample surface. This is one example of how the contact mode works in measuring the shape of sample. First, it takes physical contact with the sample, and we got this force as a set point in this measurement. At the plane area, there's no big difference, but when the tip meets the uphill-like feature, distance between tip and sample gets smaller and the repulsive force applied on the tip gets bigger. So the feedback makes the z-scanner up to maintain the set point. And when it meets the downward slope, distance between the tip and sample increases, so the feedback makes the scanner down to give more force until it meets the set point. So finally, we can get this topography information of the sample. Summarizing the contact mode, it uses the repulsive force for feedback, and the tip has a physical contact with sample, which can damage both tip and sample. Force is used as a set point in contact mode, and the feedback maintains that constant force by moving the z-scanner. But actually, contact mode is not a good way to image the topography because of its physical contact. It can cause some deformations on the sample surface. But however, it is a very basic method to measure many of advanced modes like conductive atomic force microscopy or some piezo force microscopy. The next one is non-contact mode. So non-contact mode uses the attractive force, but it is so small to detect and it cannot bend the cantilever like repulsive force of contact mode. So instead of using force, we use amplitude near the resonance frequency for the set point. Here is the resonance frequency curve of cantilever, which has no interaction with sample surface. But when the tip gets closer to the sample, attractive force starts to increase, and it decreases the effective spring constant and the resonance frequency at the same time. So it causes the shift of the resonance frequency curve like this. And at the point of the driving frequency, the amplitude decreases from A0 to A1 by the curve shift. So we use this phenomena for feedback in non-contact mode. In non-contact mode, the amplitude of the cantilever at resonance frequency varies with the magnitude of attractive force between tip and the sample. For example, when the tip gets closer to the sample, due to the increasing of attractive force, the amplitude just decreases like this. So we can choose the proper reference amplitude when we measure non-contact mode. This is the scheme and procedure of non-contact mode. First, the AFM cantilever oscillates mechanically at the resonance frequency to detect an attractive force change between the tip and the sample. Second, the feedback moves the z-scanner up and down to maintain a constant amplitude and distance from the sample without touching the surface. Third, the z-scanner position follows the sample surface like this. As like contact mode, I just prepared an example of measuring the topography with non-contact mode. But before the explanation, this oscillation is not real actually. I just exaggerate the oscillation for easy understand. And when the tip gets closer to the sample surface, it feels the attractive force and the amplitude of the cantilever decreases compared with no interaction state. Now, we use this amplitude as a set point in this measurement. When the tip meets the highest structure, distance between the tip and the sample is smaller than that of initial state, and the amplitude gets lower. So the feedback, which wants to maintain the amplitude at the constant value, makes the scanner up to get the amplitude back to the set point. And when the tip meets the downhill slope, like this, distance increases, so the amplitude gets larger than set point. And again, feedback makes the scanner down to maintain the constant amplitude. And this trace is the result from the non-contact mode. So non-contact mode uses the attractive force, but it is quite small to detect, and it cannot bend the cantilever directly. So that is the reason that we use resonance frequency and choose amplitude for our feedback. And feedback just maintains the constant amplitude by moving the scanner up or down. And there are no tip and sample damage because there is no physical contact between two of them. The last one is tapping mode. Tapping mode is also called intermittent contact or the dynamic contact mode. It uses the cantilever oscillation for a feedback as like non-contact mode, but the tip makes the intermittent contact with the sample like this. So it just literally taps the sample, and that is why it's called tapping mode. So once again, in non-contact mode, there are no physical contact with the sample, but in tapping, the tip continuously taps the sample surface. Also, tapping mode can measure the relative mechanical properties of the sample. The phase lag between the drive signal and tapping signal contains information about the relative mechanical properties when we use tapping mode. In tapping mode measurement, the base theories are totally same with non-contact mode. But just one difference is that the tip makes an intermittent contact with the sample like this. And when the tip meets some height, distance between the tip and sample gets smaller, which means the amplitude goes down than initial one. So now we all know feedback makes it back to the set point with adjustment of the z-scanner to the upward. So in opposite situation at the downhill, amplitude gets bigger due to the increasing of the sample distance, tip sample distance. So the scanner moves down to bring the current amplitude to the signal, to the set point. So it draws the topography like this. And if the materials are different in A and B area, tapping mode can get relative mechanical properties between these two regions by its phase image. So basically, the tapping mode uses cantilever oscillation, just like non-contact mode, but the tip makes intermittent contact with the sample. Because of this, both tip and sample can be damaged. And we also can get the relative mechanical properties of the sample by using a phase image of tapping mode. So sum up all the kind of three different basic AFM modes. In contact mode, the AFM tip physically contacts with the sample surface, and generally it is not recommended for just imaging, but it can utilize for option modes, such as conductive atomic force microscopy and piezo force microscopy and some mechanical properties measurement. and non-contact mode, AFM tip does not contact with the sample surface, so it is for the most of AFM height imaging. And last one, the tapping mode, it has some same principles of that of the non-contact mode, but in tapping mode, AFM tip has an intermittent contact with the sample surface, so the relative mechanical properties can be obtained in the phase image. So now we will see some simple examples of the images which are measured by three different basic AFM modes. This is the example with gold-coated mica substrate before and after AC reaction. Usually we use soft tip for measuring the contact mode. The reason that we use the soft tip for contact mode is to prevent the indentation or plastic deformation of the sample by some physical contact. So, as you can see at both height image, before and after AC reaction is well measured with contact mode. This is the image from the non-contact mode. So some funny features imaged and tiny dots on whole sample surface also well detected by non-contact mode. The sample of gallium nitride film. So in 1 micrometer skin size height image, we can see some detail feature which is not observed well in 5 micrometer skin size height image. And argon film, which is also measured with non-contact mode. So with using AFM system, we can get the 500 nanometer size image with a good quality as like the image at the right side. And it is also possible to get more smaller size image with some small scan. This means that AFM can help us to explore the nano world from the range of the few micrometers to the nanometer size. This sample is the height and the phase image of MOS2, which is measured with tapping mode. As you can see in the phase image, it makes a beautiful contrast between MOS2 grains and the substrate. Like this, the tapping mode, we can get relative mechanical properties of sample as well as the height image. This is the result of F14 and H20 with tapping mode. Height image and phase image look so clear, and we can see the relative mechanical properties in phase image as well as MOS2. So this is the end of my presentation for the webinar. It was so great honor to make my own presentation for the first time. Thank you so much for listening my speech for principles of the basic AFM modes, and I also feel so much thanks for many hands from our team. Hope you all can get gorgeous images with using these three basic AFM modes. Thank you.
Okay, Chris, seems we have our questions now. So for our first question, what kind of sample is suitable for non-contact mode?
So actually, we use very see the roughness of some kind of sample with the contact or non-contact mode or tapping mode, but we can actually get the very steep height of the sample. But we can get some almost of the samples of the height, except the kind of so steep height sample.
Okay, thank you, Chris. And then what kind of information can you get from coating or polymeric films?
Can you pardon?
Okay, Okay, I'll repeat. What kind of information you can get from coating or polymeric films?
Polymeric fields.
Yes, or
Um,
coating. What kind of information can we get?
so I can't understand the what field. I didn't hear actually.
Okay. Maybe for the one who asked this question, can you send us a more, can you elaborate the question, please? And
Okay.
then, so we will move to our next question. So we have a number of questions coming. So
Okay.
during the pre-scan setup, what is a good shape of the amplitude
So
and
the
phase curves? Sorry, and phase curves. I will repeat, during the pre-scan setup, what is a good shape of the amplitude and phase curves?
um actually the amplitude, the phase curve, we can get the very sharp and very clear shape of the amplitude at some kind of non-contact sweep. So we can use it at the non-contact mode for imaging. And so, yeah,
Okay, thank you. So a lot of questions are coming. So maybe we'll get our last two question, and then the other question we will answer them via email. So
okay.
what are the typical applications of AFM in adhesives?
Some we can use AFM. We can see some kind of the electrical properties like with a conductive AFM mode or some EFM or some KPFM things, or we can see more magnetic field things with the MFM, magnetic force microscopy, or we can see some many things with it, with like a PFM piezo force or some uh, mechanical properties with it.
Okay, thank you again, Chris, for that explanation. And then for
Yeah.
our next question, how maximum feature height can be measured by these modes?
But actually, there are no kind of some limitation because when we use the tip with the high aspect ratio, we can get the image of the bare bead height of the sample. But when we use the very dull tip or some short tip of when we use AFM, we can get just kind of that height of the image of the sample. So when we want to get some more height image, we can use some kind of some sharp or some long tip for measurement for the AFM system.
Okay. Thank you, Chris. And I'll pick our last question. Is high frequency tip or low frequency tip suitable for tapping and surface roughness measurement?
Yeah.
I will I will repeat. Is
Yeah.
high frequency tip or low frequency tip suitable for tapping and surface roughness measurement?
The you means the frequency of the non-contact mode, right?
I think so. It's is high frequency tip or low frequency tip suitable for tapping? I think he's asking which is more suitable for tapping. Is it high frequency or low frequency tip? For
Uh,
tapping and surface roughness measurement.
it is quite so when we use the non-contact mode, we actually use kind of the high frequency because the cantilever is very soft, so hard when we use the non-contact mode like AC 160, and we use it for about the 300 kilohertz about the frequency. So the we use at the kind of, but there are so numerous cantilever which has so kind of various some frequencies. So we can choose one of them when we want to measure some sample at the proper state, proper situation.
Okay, thank you, Chris. So that will be our last question to be answered live. But you can continue to type in questions as we wrap up. And if anything comes in, we will reach out to the attendees via email afterwards and answer all those questions. So if
Okay,
you want
sure.
to know, yeah. for our attendees. For those who ask question, you can continue to type in your questions, and for those with question who have answered already, if you have follow-up questions, you can still type in your question, and we will answer all those questions via email.
Okay.
So thank you for your questions. Again, thank you, Chris. So if you
Okay.
want to know more if you want to know more information about Park Systems AFM and an upcoming Park Systems webinars, please click on the events menu at parksystems.com or follow Park Systems on Facebook. Or if you have any interest about what other video materials we have or any other webinar sessions that we have done, please visit Park Systems YouTube channel. And for any AFM related questions you have, please direct it to inquiry at parksystems.com. So that I think that's will be all for now. So with that, on behalf of Chris and the rest of the staff here at the technical marketing team for Park Systems, thank you all for making time amid your busy schedules to join us here today. It's been our pleasure to host this webinar, and we hope to see you again at our future webinars from Park Systems soon. Have a good day, everyone.